Alright, welcome back, guys. Uh, just a minute. What we were building, right? Yesterday, we already built this two functions, count pairs, right? And one was to initialize the vocabulary, right, from the corpus. And what we did was we took the word and the frequencies of those words, right, and as the key value pair. Then what we did was sim- symbol is equal to we like listed out them as uh, characters. Then we add the end also in the list, and we build the tuple of out of that. And that tuple can be used as a key in the dictionary. So here we used that key, the symbols of the tuple as a key of this dictionary vocab, and the frequency of the corpus items as the value here, right? Then after that we take this vocab here dictionary, and we initialize a counter dictionary called pairs, right? We will count the pairs in this, and we loop through this vocab dictionary, and take the symbol tuple and the frequency value here. From this tuple, what we did, symbols and symbols plus one, we make the zip then and make the pair of out of it, right? Take the pair a comma b there, and a comma b we are also using as tuple a comma b, and we are using it as key, and we increasing the frequency of it, right? This was uh, the count pair thing, right, guys? Let me do the one thing more. Okay, alright. Yes. Next thing, guys, we will do is right. This is what we will do, and next thing we have to merge the pairs also, right? That's what we have to do. These are the pairs here, and then we have to merge these pairs, whichever the winner pair in this, and then we have to merge that pair and update the corpus, right? So we will define a function, right? We will define a function def merge pair, right? Vocab and comma pair. Vocab also a dictionary, guys. If I want to type into here, right? This is pair is also dictionary. These are of different type, but okay, both are dictionaries, right? We will like when we solve this, we should follow the standard thing, right? Now this is the actual BP learning operation here we are doing. Suppose there is a pair u comma g, right? So let me write that also. Let me write it. Suppose there is a pair, right? One is u and one is g in the pairs dictionary, right? So then if I put one thing, if I say okay, a comma b is equal to pair, what does that mean? If I assign pair or like open it to this assignment a comma b operation, then this will do a is equal to u. This will automatically assign b is equal to g, like this. If I do this operation, guys, right? And then I can merge it, like I can say okay, here also merged symbol is a plus b, then it will become ug, isn't it? Right? So u plus g will become ug here. It will be concatenated. So then we create our new vocab, right, guys? And like it will have this not the separate thing as u comma g, it will have ug as single entity or token in that case, right? So we will create new vocab. Why we create here new vocab? Because we don't want like to destroy the original structure, right, while we are still processing it. So we want the original structure because we haven't processed it, the original structure yet completely. So what we do, we build a new representation, right? So alright, so let me create here also like new vocab, right, guys? Isn't it? So just a minute, I am looking something if I am correct or not. Right, guys? So here what I can do is a comma b is equal to, I can assign the pair here, right? And then I can do is like okay, what is the merged symbol, right? merged symbol will be, right? Symbol will look like as a plus b, right? And then we will define our new vocab dictionary, right? Here, and now I will iterate through vocab items, right? And whenever I get this thing, okay, like now I can like loop through each word, right? Like for symbols for frequency in our vocab, right? Dot items, right? So what we will do, this vocab in the representation of we have pairs as a dictionary here, okay, and we have the vocab of characters, right? So this is the symbols are the character, this is the old vocab of character label tokens, right? So then we will have our new symbol, right? It will be a list, like it will store the merged results, okay? I is equal to 0, and so this I pointer will point through the sequence, okay? So while I is less than length of symbols, right? It will loop through each sequence and of the symbol, right? So it will keep processing the symbol which is looking like let me explain. This one symbol is looking like this, guys, like H U G and end of the word. One symbol look like this tuple, guys, okay? So you can imagine like how it looks like, right? So it will look through the symbols, and then if I is less than length of symbols -1 and symbols I is equal to A, guys, right? And symbols I plus 1 is equal to B. In that case, what we can do, like this, we are checking that if A or B are like this merged, similar to the A merged symbol, right? So then what we can do is, like if current symbol is A and the next symbol is B, for example, it is like symbol I is U, right? And symbol I plus 1 is G, right? So we are checking this, if it is U and B. If yes, then we will merge them, okay? So what we can do is new symbol is our list, right? Or you can say like new symbols, not symbol, right? New symbols dot append, this is a list, right? Merged symbol, right? So here it was U comma G, now new symbol becomes UG, right? And then what we will do after this, if it is true, then I plus is equal to 2, right? So we have to jump to for 2, like not 1, like I plus 2. From I we have to jump to I plus 2, right? That is the case because we consume the both U and G, right? So like we don't want to process them again, right? Uh, Else, like in the else case here, what we can do, new symbols dot append symbols I, and I plus is equal to 1, right? So in the, if it is not like that, then if it is not equivalent to the pair, right, then new symbols will be this list here, right? So this position doesn't begin the pair, right? So we want to merge. So keep the current symbol as it is, right? And move forward by 1 only. And next thing, next finishing touch will be like this, because we processed the one symbol, right? One symbol completely. Then what we will do is in this indentation here, in the indentation of right here, right, what we can do is new symbol, no, the new vocab, right? New vocab will have this tuple of new symbols, right, is equal to frequency, right? Whatever the frequency of each of it will get that frequency, right? And net, and the end, what we will do in the indentation of 4, we will return new vocab. So it will return the updated vocabulary representation, right? Do you understand it, guys? Do you understand that, right? We take a comma b is equal to pair here and merge the symbol, right? Is equal to a plus b, and then okay, let me हेलो कहाँ पे भाई OBS पे हो? Yeah? 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 हाँ OBS आ गया 1 मिनट में 1 मिनट बस Alright guys, you understand what I did here? Do you understand it? Alright guys, you understand what I did here, right? Though this is the similar thing, okay? Right. So first I did what I did. There was a pair, right? Which pair? Uh, there was a pair here, right? And here the pair is like not dictionary. I think it's just a tuple. So I will not uh, it's any, right? I will not type into it here. Then those pair symbols are assigned to a comma b, and I merged those symbols as a merge symbol. Then I went in the symbols and frequency of the vocab, original vocab. Then I needed new symbols, right? So I need new vocabulary and new symbols, both new, right? So I is equal to 0 here, and so when I am processing one symbol, if length is less, I minus 1, right? And symbol size is equal to this, then what I will do, I will new symbols, I will append the merge symbol here, right? Whatever it is, and if there it is, and I plus is equal to 2, I will go ahead, right? And whatever the new symbol is, else new symbols append vocab symbol I, right? So whatever the new symbols is here, right? I will assign the frequency of to all of them as a tuple, and frequency will be the same as before, and I will return the new vocab. This is very nice explanation, and implementation also very clean, right? Now we will train our byte pair encoder. Okay, so here so what it will do, that this will be our whole BP training loop, right? So in this, each iteration will add one new subword token, right? A merge rule, and the final vocabulary we will get, right? Like final vocabulary we will get, like it will contain original characters plus all merged symbols, right? Then we will return merges, right? The order list of merge rules learned, right? So this is very important. We have to return the ordered list of merge rules which we have learned, right? And the vocab, the final symbol sequence for display, right? So let me implement this function, which is this. Okay, one more, I think one thing I left in this was what this function do, right? This is very important in Python. So this function do, like it glue two symbols of pairs, right, into one new symbol, right? So it glue two symbols of pair in one new symbol, right? And also, like, this is actual learning step, right? Like here new symbol will become the token, right? Also one more thing I can add here, like by the example, right? Like if pair is u like this, like this is u, right, comma g, then the this tuple, right, like h comma u comma g comma end of word, right, will become, right, what it will become, this h comma ug comma end of the word, right, this isn't it? It's very important, guys. Now what I will do is I will define a function def train bpe, right? We will take the original corpus and number of merges equal to 3. For now it is default, right? Like this is the complete training loop. Like the complete idea here is like first we will count the pairs, then we will find the best pair, right? After finding the best pair we will merge that pair and it will repeat, right? And number of merges will be 3, means like here we will perform only 3 merge operations. Okay, so let's initialize the vocabulary first, like so vocab is equal to just a second. We have this function, right? Init vocab function. What it will take? It will take the corpus as input, right, guys? So just a minute. Okay, let me initialize the vocab. We have this function, right? Init vocab. It will take the corpus dictionary from us, right? So let me tick init vocab and I will corpus inside, right? So it will convert the words into character sequences, right? Then we will have our merges also. It will be a list after all the merges. This list will store the whatever learned merge rules we have, right? So like after the merge, initially it is empty, after it will learn things, right? Like here this list initially it is empty, right? Now after learning it will contain like this u comma g pair comma u comma n pair, then n comma this w pairs, like this. It will contain this merges. This order list is extremely important. Okay, this is the actual learning for tokenizer, right? So this is the list the tokenizer will use later for encoding also. So this is very important, right? Here you see this is not merged, now it is merged here, right? So all of the sequences, all of the merge sequence it will contain. right? Now then I will rest we can print something here like start each word as characters, right here. So what can I do? I can try if s comma f and vocab dot items. What is s and what is vocab here? You see, vocab is a character list, the characters, right? So tuples and characters. So here, this is the symbol and this is the frequency. S we are like shortcut here. S is like symbol and F is frequency here, right? Then I will print something here. So also I can print that, okay, like this, like print f string here, right? And what it will do, it will right dot join so and frequency is equal to f here, right? So here what it is doing is it will like so it will like print us every character in a word form, okay? Every word in a character form actually, right? This this is what it will do. This is a space, right? It will go to S and it will put space between each character, okay? 20 character space, right? Then frequency it will have, okay, in the each tuple, right? That is what it will do. And after it, what this is S, right? This is S, this input here S. Join S and put a space between each character. This is a tuple here. Alright, then what I will do is here I will go for step in range of number of merges. What is this? Like how many merges we need? We need 3 merges, right? So which step we are doing? If number of merges is 3, we will perform like step 0, step 1 and step 2, right? 3 merges total, right? So how many merges we have to take? 3 only, right? So pairs equal to count pairs, right? And we will give it the vocab to it. Where is the vocab we get? We get the vocab from here, right? Character level vocab, right? We have character level vocab, then we count the pairs, right? Count pair function we have here. So this takes the vocab, right, as a, and pairs is the counter. It will take the symbols as a tuple and go inside a comma b and zip that and count all the pairs, right? So here pairs we have, it will also return a dictionary, I think, with pairs, right? So it's also pairs also a dictionary here. So it will count all the adjacent pairs, right? Then what I will do is like if not pairs, what I can do, I can break the loop, right? Like if there is no pair left, so we will stop in that case, right? Now what we have to do, we have to pick the most frequent pair, right? And after picking that, we will return the pair with the highest count. If several some tie, then Python will return the first one it encounters, right? That is our deterministic tie break here. Real libraries also do the same kind of deterministic route, right? So what I can do is I have to choose the winner, right? Like best is equal to max of pairs, comma key is equal to pairs dot get. What it is doing, like it is doing, this is very important. Let's say pairs contain like this. Some pairs have this key and value, right? Let's say this is our dictionary pairs, right? Pairs dictionary. It will have, let's say, u comma g as a tuple is equal to 20. Then it has p comma u as a tuple is equal to 17, like this, right? And u comma and let's say it's a 16. So let's say this is our pair dictionary, right? So max will find the key with largest value, right? So best is UG here, because 20 is the largest frequency here, right? And like if some ties, right, Python will return the first one it encounters, that is our deterministic tie break. So let's say we have something like in this only, right? If we have something like un is 16 and n comma end of word is also 16. So like here both have same frequency, right? So code still needs to choose one in this case. So our implementation will use deterministic order in this case. That means like rerunning the same code with same input gives the same result here, right? So yeah, what I can do here is so based on the value, highest value we have, right? Pairs dot key, we have to return the pair here. We get the best pair here, right? And then what I can do is I can print something like merge step 1 and most frequent pair is this, right? And count pairs best is this, new token will be like this. So we can do many things here, right? Print here. So I can print, okay, print string slash n, right? It is the merge step. Merge step is step plus 1, right? This is our step, and I can say like, okay, our most frequent pair, right, is the best, right? And again I can do is like this, count, right? Count is this, okay, count is we have pairs dictionary or best, whatever the count it is, right? And then we will have what will be the new token, right? New token, or I can write like this in a one token form here also, right? New token is here, like best 0 and plus best 1 here, and I can problem this like that, right guys? And here also that is it. Then after it, what I can do is I can merge append it, right? Like merges dot append is best, right? So this is our list merges. We have this first rule here, right? Our pair. So we will record the rule, right? Then what we will do is we will have like a new vocab, right? So our new vocab will be like this. Vocab is equal to merge pair, right? We will vocab comma best pair, right? We are then after that we can, this is our new vocab now, vocab whatever vocab we get, right, after the first merge. Then I can show the new vocab also, like for S is a symbol, F is a frequency, in vocab dot items, right, here. Then whatever it is, like I can print F like this, and similarly like join, right, S, right, 20 S spaces, and the frequency will be F, right? This will show the vocabulary after the merge, right? Then what I can do now is after this training loop, okay, I can return the merge list, right? Merge pair list, and and remember, this is very important here. What we did, merge dot append. Best was, let's say our best pair was u comma g, right? So this matters because later when we encode new text, so we need to know what merges we learned in what order, right? Right, and after that I can mm, okay, so this is our merges list, right? Note the merge pair, merges, comma, vocab we have to return after that, whatever final vocab we have, right? Merges rule and vocab of the training, right? So yeah, now what we can do, like we will define a function which will encode a new word using the learned merge rules, right, in order also, right? So we should have, like, def encode, right? Like we will have a new word, and based on the merges rules, we will like tokenize it, right? So what it will do, it will tokenize brand new words based on learned merge rules, right here. And this is exactly what a tokenizer do at inference time, right? This is very important, guys. So yeah, this will we have some symbols, right? First we will split this out, right? Symbols is equal to list of the word, right, plus end of word, right? This is our symbols. Then we can convert it into tuple or something like that, right? So for a comma b in merge, right, it will give us pairs, right? Apply each merge rule in certain order, right? So we will have this I is equal to 0 iterators, and then we have our new symbols, right? Whatever new symbols we get after that, right? Then we will also convert it into tuple, right? So while I is less than length of symbols, right? In that case, if I is less than length of symbols minus 1, and symbols I is equal to a, and symbols I plus 1 will be, right? In that case, what we will do is new symbols, right, will append here a plus b, right? It will be like merged symbol, and I plus is equal to 2, right, guys? And else new symbols dot append symbols I in that case, and I plus is equal to 1, right? Then this is one first iteration, right, of the one symbol, first time. Then after this new symbols we get, that after this new symbol here, right, then symbols is equal to new symbols, right guys. Then we again do this like then we have this, again we have this symbol, right, symbols. Then we again go into the while loop here, length of symbols, then like I is less than A and B, whatever it is, right. Right, and then after that we will return the symbol also, right. Return symbols, okay. So first we will apply like merge rule 1, then we apply merge rule 2, then we apply merge rule 3, like because we have three the order matters, right. Like for example, u plus g will become ug, it must happen before another rule might use ug, right. Like something like h comma ug could be the next rule. To like go get that next rule, we need to first make the ug first, right. Then we can make h comma ug before we have to make u comma g as ug, right. So merge list is the ordered here. This is very important also. This is why we do append here, right. So after each merge, right, this merge has happened, right, and like one pass is gone. First rule we already applied, first rule, right. We applied first rule already and we got the merge. Then this is very important that we get the next rule must operate on the result of the previous merge, right. So then finally we will return symbols here, right guys. And after that we will have our main function, right. We will define our main function, and this will run the demonstration for us, okay. So it will print first statement, like we can print something like this, okay. Training BPE, right, to match our day to end written, right, example here, right guys. This will tell our code it reproduces the whiteboard example we already did, right. Then we have our merges, we will get our merges, right, merges comma final vocab. This will go to the train VP will return it, right. So corpus will go inside it, corpus, and number of merges equal to 3 we are passing here also, right. So after this we will receive the merges and the final vocab. Merges is the rules, right. Then what we will have is we can print something like, okay, learned merge rules, this order list is the tokenizer, right? So we will get the merge rules, right? Whatever the, so we can print uh, these our this is our learned merge rules, right? You can say this ordered list is the tokenizer here, right? This is very important, guys. You can confuse, like, okay, our final vocab is the tokenizer. No, this merge rule is the final, like, tokenizer for us, right? So for I comma m, right? I comma m in enumerate merge is comma 1, right? So in, like, what enumerate will do, enumerate will numbers the rules starting from 1. Okay, so like rule 1, rule 2, rule 3, like that, right? So one will correspond to something like that. So enumerate will do that for us, and then what we will have is print statement, right? Print f string, right? I is the enumerate number, right? I think, and m0 our merge 1, right? Plus m1, right? This will give us m0 plus m1 here, right? We can write it like this, right? Then after that, what we will do is encoding examples, right? We can encode something like this, and encoding examples demonstration, right? For W, so it will be like for W in HUG, comma PUN, right, comma GUGS, comma BUGS. We can like look into it, like, okay, in the list we can pass one by one and check, okay, what is the encoded encoded version of this, right, of subword, right? So we can print print f, right? This is a W, right? 6 space, let's say we are giving it the space here. After that, then we have this encode W we are giving, and merges we are giving the rules also, right, to this, and yeah. Now at the end, what we can do is okay, so if name, right, equal to main, then it will be our, not like this main, okay. Then we can do it, and right, should we run this, guys, now, right? We should run this, like we have put very much effort in this. we have put it like very much info this. So source and LMA VNV here, right? Then activate. What happened? Okay, source LMA we then activate here and what? Oh, source LMA dash here, right? When okay, we have this and Python where okay Python, right? Day02 slash BPE from scratch dot py. What happened? List word, list that word. Where is the can only concrete list, not str. What? Where? Line 143. Line 149. What is the problem in this? One 10 here list word and what is the problem here, guys? It should be similar like this. Okay, here we have to because it can only concrete the list, not the string, right? So this is it was what it was saying. Okay guys, let's see what is the magic happened here. So we are training our VP to match our day 200 an example. Start word. So HUG it like done this, right? And 10 PUG and learn merge rules. This order is the tokenizer and coding example demonstration. Okay, where is the print in that case, guys? Where the print went? What happened here? Enumerate merges I, right? So this pre statement is running, but it is not running here. Why not? And the demonstration is good, but I think there is no learning also, right guys? Where is the learning went? What? So if I want to Okay, what is the problem here? Init vocab count pairs. This is pairs counter. Okay, so we can return it here also, like return pairs as a counter, and all right. Oh, it's like look more good. So this was a character level, right? So merge one rule was this, right? Most frequent parent is UG here. Count is 20. New token is UG. You can see here H comma UG frequency 10 like this. So it like merged it them. Then after merge 2, it was UN also merged. Then the end of word UN and end of word is merged in this merge 3. These only 3 rules, right? So learner merged rules, this order list the tokenizer. So UG plus UN and U plus N is UN. This 1, 2 and third is this, right? So this encoding example demonstrate HUG, H comma UG here, PUN like this, hugs like this and this. So what a beautiful demonstration of a tokenizer, guys, here. Do you understand it? What a beautiful demonstration here, right? Alright, just a minute guys, I have to do something for a minute, then I will continue, okay? Alright guys, it's worked. So I was just doing a problem, so it works. So thank you so much. Next, what we will continue, guys. Okay, you understand this? What it we already built, right? Very important it is, right? Right guys, so do you understand it, like how this most frequent things and how all of this learning is happening, right? And the rules are also there, like whatever the first rule here is, you can see, right? You can see when we write the rules, which merge pair and merges train VP we will have after this merge, right? So whatever the best pair we get, right? This will be the first order of our merge rule, right? The topmost we get, that is our first rule here. You can see also here, right? We have this merge rule here. U plus G first is the top best pair we found, right? Then we found UN as a best pair, right? Then we found the UN as a best pair, UN comma W, end of the word, right? So that is very important. And next thing I will tell you is, just a minute. So this is our the handwritten tokenizer, right? So we need our real tokenizer also, right? Because this is what we are building the project for. Okay, so like that will not be like only
वापस देना है. तुम उसको रिस्पॉन्ड नहीं कर रहा था।
So let's guys continue further this, right? So we already trained our hand made tokenizer, right? Now we have to train our tokenizer for like large data, right? And we have to run the real okay, so just a minute, we will continue. Let me get something. Okay guys, so now we will train our real tokenizer, right? Like we already developed our from scratch implementation, right? It is good for understanding purposes, right? But we are not going to train it like, okay, 32,000 token in which is multilingual also, right? Can we develop this multilingual tokenizer with our slow educational this implementation, right? Because real corporas are huge, right? So we will use like already developed Hugging Face tokenizer and something like that, right? These libraries will provide highly optimized implementations for us. Okay. And the original project described this as using the Rust backend tokenizer for the production grade version, right? So here we are not using the library to avoid the understanding of byte pair encoding, right? Like we already implemented here, right? So we are now using the optimized implementation to scale the exact idea to our real data, right? This is very important engineering distinction. And so we developed our from scratch also. This was for understanding purposes, right? Now we will use the tokenizer library for scaling, right? Today we are not using any GPU. Like tokenizers, we can train these on CPU only. Like this is just CPU work, right? Like this tokenizer training can run on laptop, like you can run it on Colab, you can run it on Kaggle, anything, right? So what we can do is we will create a new file, right? Here train tokenizer.py like this, right? And so it is about like we will train the real tokenizer here, right? With 32k tokens, right? We have 32k tokenizer here, and it will contain some Hindi and plus English plus some Marathi also, right? So we will use it will be using our Hugging Face, right? There is a Hugging Face tokenizer already, right? So tokenizers, like this is same as BP idea, so just fast and production grade here, right? So what I can do is I can install this tokenizers. So pip, let me do it, clear pip install in our module, right? Tokenizers. Okay, so it's getting it, right? Alright, so everything this file will train the actual tokenizer for us, right? Hindi, English and Marathi with like something about 32,000 vocabulary entries, right? What I can import here is import argument parser, and I can import JSON from pathlib, import path. We have to like get the data, right? The corpora also. So this argparse is used to accept the command line arguments. Okay, for example, let's say I am writing a Python train of tokenizer.py with some file. There is any data, right, in the file. So we have to get the from there. To accept the command line arguments, we have to import this argument parser, right? The script will need to understand those arguments also. Then JSON, this we are using JSON to save our vocabulary in like dictionary format, right? JSON format, and the special token mapping, validation report, these things. Okay, you will understand when we will reach those. And path, we are importing like it will provide us a clean way to work with file paths. So yeah, that's then from our tokenizers, right? I can import tokenizer here. So what is the problem here, guys? Import token not resolved. So I think I need to do some. Okay, I need to select the interpreter, which is my interpreter here. Then I think it can, yeah, now it is good to go, because we already installed the tokenizer from the Hugging Face, right here. So it is now referencing to this, our local virtual environment as interpreter. And So you can think of it like as the object, right, that will hold the complete tokenizer for us. Okay. Next thing what we can import like from tokenizer dot models, we can import the BPE model, right guys? So this will select the BPE model itself. Next thing what I can select from tokenizers, right, dot trainers, I can import BP trainer, right, BP trainer, right. This will provide the training algorithm for us. And the next thing is from tokenizers dot pre tokenizers, right, we will import white space, and we will import the punctuation and sequence as pre-sequence. Okay, what I did here, right guys, these will determine how text is split before we put it into the BP training, right. Next what I can do is we can import from tokenizers, right, normalizers, I can import NFKC here, and sequence as norm sequence. Okay, so these things will handle our Unicode normalization. This becomes especially important for Hindi and Marathi for us. Okay, this Unicode normalization. Okay, and then what I will have now, one of the most important section is here is the spatial tokens. Okay, some will have like spatial. After importing, now we will define spatial tokens, right. This is our spatial token here, right guys. So the idea is we decide the spatial tokens before training. Okay, so just a minute. Right, so we have to decide like what are our special tokens will be before training them. Okay, why? Because once the vocabulary is constructed and the token IDs are assigned, okay, then adding special tokens later can create like engineering problem, right. So we reserve them now, right. So these original tokens are like this. First is UNK, right. Unknown, right. And next will be this unknown is for unknown token here, right. If something cannot be represented, right, by the BP tokenizer, right, so this will be fallback to this. This is the fallback for it, right. So we want the number of unknown tokens to be extremely low, because we want to represent everything as like maximum possible, right. We want to represent everything in our vocabulary. So the less unknown that is, it is better, right. Then we have this padding, right. It's a padding token for us. Suppose one sentence has some 5 tokens and another has 8 tokens, right. So to put them in a same batch of training, when we train, we may need to pad the shorter sequence, right. So 5 tokens and 3 paired tokens will make out to 8 tokens, right. So we will use this later around data batching. We will understand that. But okay, next is we have S. This is will define the beginning of the sequence, right? Like we understand this on day one also, like beginning of sequence and end of the sequence, right? And then we will have this as also, this is the end of sequence, right? Then next thing we will have is mask. Mask is like reserved for masked objectives or like future use, right? So our current language model is auto-regressive, so we may not need it for core pre-training, but reserving it for flexibility, right, gives us flexibility. Then we have SEP. SEP is like separator token. Okay, it is useful when multiple pieces of text are combined. For example, like input, separator, then output. So this will become useful during fine tuning for us. Okay, we will understand that also. So fine tuning will be later, and separator token is here, right? Right. Then guys, we will have the language ID tags. Okay, so we can prepend which language a segment is from, right? Like it is from Hindi, it is from English or Marathi, right? So language ID tags we have to define also, right? So one is English we are using, right? We have to tell it, and one is Hindi we are using, right? And one is Marathi we are using, right? So this is that, and as a language tag can be placed before a segment, right? Like this tag, then hello world, like this, right? Or like HI tag, then namaste everyone, like namaste log, namaskar, like that, right? And MR like Marathi, namaskar jag, like this. So this can provide like explicit language information to the model also, right? Then we have chat tokens, like this chat, when we chat to the user, so it can be user, right? You can be assistants also, like assistant, right? So these are the intended for instruction style fine tuning, right? For example, the user says, okay, translate this to Hindi, then assistant will respond, right? So we will encounter this concept later around fine tuning also. Okay, then we have task tokens, like switch and no switch. What is this? These are for like code switching detection, right? For example, the model could classify whether a sentence contains a language switch, right? Then or not, right? Then we have it is reserved for like spelling correction. Okay, so these task specific tokens are being served now, even though the actual fine tuning happens will later, right? So this is important design principle, like plan the vocabulary early, right? Because once the tokenizer trained and it gave the like index numbers to all the vocabulary, right? Then token IDs are assigned to all the tokens. Then adding a special token later can create engineering problems, right? We learned that. So we are planning this early as possible, right? That is it, right? So that's it. This is our special tokens, right, guys? So you have maybe like questioning, okay, why not simply add these task tokens after training? Because the vocabulary correspond to integer IDs, right? So the neural network will eventually have an embedding matrix like this, like this, like you have token ID 0, you have token ID 1, something like that, token ID 31,999. If you have 32k token vocabulary, so each token will have a ID. Okay, so if you modify the tokenizer vocabulary later, right, so you may need to change the vocabulary, right, you need to change vocab, you have to change the IDs, right, you have to resize the embeddings, all the embeddings, right, because each of that will get the embedding, and potentially you have to retrain also, because it may be like different tokens all after that, right, potentially retrain, right. So reserving the tokens up front is very cleaner. Alright, so build the tokenizer object. Now we will like define, let me give value, define build tokenizer, right. So what this function will do for us, it will assemble to us the BP model, right, and the normalizer and the pre-tokenizer also into one tokenizer. Okay, so here what we will do is let me tell you this, what it will do, right. What happened guys, it will assemble the untrained BP tokenizer for us, right, BPE tokenizer, which is configured for 3 languages, right, and or you can say 3 script, and the normalizer and the pre-tokenizer, right, choices are what make it work for Devanagari, right. Devanagari like Hindi, Marathi as well as Latin English, right, like Hindi, Marathi as well as for Latin, which is English, right guys. Okay. Now what we will have is we will define the tokenizer object. Here is we will initialize tokenizer, right, unknown token equal to UNK. Here we are passing it, right, and we are taking the BP tokenizer inside it, right. Yeah, okay, that is it. So this BP mean here is like use the byte pair encoder as a tokenizer, right, and UNK means like use UNK when something cannot be represented. So we are passing our specific token, right, special token. So this tokenizer, what will do, it will wrap the model into full tokenizer object for us. Okay, then we will have this thing. Next is tokenizer dot uh, well, this should be like this. Okay guys, tokenizer it is. Okay, that's the tokenizer. Then normalizer here from tokenizer object. Normalizer like norm sequence, take this, and what you have to do is NFKC. Okay, so like it is, we are saying like use NFKC Unicode normalization. Okay. So this will use this tokenizer will use this normalizer, which is NFKC normalizer. Okay, Unicode normalizer. What is normalization actually is? Like before tokenizing, we may want different Unicode representation. What is Unicode representation? Give a number to every character like this. Okay guys, so Unicode representation is of visually equivalent text to be standardized, right? So imagine two things look the same on screen, right? Let's say this is a, both are look similar, right? But they can be encoded differently internally, right? So without normalization, if tokenizer may treat same them as different, like. So what normalization will do? Normalization will map them into a canonical representation, right? So why we choosing the NFKC here? The original project deliberately chooses that NFKC only. The reason is multilingual safety here. Okay. So the original comment explained that the Devanagari characters can have multiple Unicode or / byte representations. Okay. So we are using Devanagari, right? Devanagari script. So these Devanagari characters can have like multiple Unicode or byte representations that look identical. Okay, and NFKC help the canonicalize them, right? So why not just lowercase? This is important for English. The dog and dog lowercasing might be convenient, right? But the project we are building is deliberately does not lowercase. Why? Because normalization choices that are harmless for English can have unintended effect on Indic scripts or their representations, right? So design choices NFKC plus we will not lowercase and do not strip the accents. Okay, this will preserve the more original language information for us. Okay, so that is why we are using this normalizer. Just a minute here. So you know this NFKC stands for normalization form, right? Compatibility composition. So this NFKC lot matters for Devanagari very much, because computers can often write the exact same visual character, right, using the completely different byte sequence. This is called the Unicode equivalence. For Devanagari, in Devanagari, vowels are often modified using like matras and nuktas, right, like this. Uh, so it is like this. When you in the you can have all right. Yeah. So this NFKC, right? So in Hindi, you have this ka and you have this ka. These are two different characters, right? But the thing is, guys, is this single ka, right? The with the character like a dot nukta there, right? Nukta dot. So as a single pre-composed character ka, as a two separate characters yield together ka and nukta dot, right? Without NKFC or BP script treats these as two completely different words, right? It splits your vocabulary data and ruins your token counts, right? So with NFKC, it standardizes both versions into exact same canonical byte sequence before counting the pairs, right? For Latin English also, English text frequently contains stylized characters like ligatures or full width characters, right? So with NFKC, it breaks down completely characters into standard Latin equivalents. For example, the ligature Fi is split into standard separate characters F plus I, and stylized text becomes standard text. Okay. And if you are confused about the what is Unicode, Unicode acts as a standardized universal numerical code for every character, right? While NFKC acts as a Lego inspector. So using a predefined lookup table for standardized different character combinations into a single canonical code, right? When processing text, NFKC identifies the equivalent Unicode sequences, such as a base letter plus a dot, and converts them into a single pre-composed character to ensure consistency in text representation. Okay. So this is the normalization here. NFKC is doing. So NFKC will act here as a smart text equalizer or cleanup crew here. So it works by using a giant built-in rulebook, the Unicode standard, right? This rulebook lists every character in a world, explain how complex symbols can be broken down or built up, right? So this is exactly how NFKC does its job step by step here. So first NFKC will look at the character and check its rulebook to see if it is made of smaller parts, right? If it is, then it will break it down, right? The analogy is, imagine you have a pre-built Lego house. NFKC takes it apart into individual Lego bricks, right? In Hindi, if you see like ka with nukta dot, right? The compatibility stripping, like it will remove formatting. Next, what it will do, NFKC looks for the fancy or weirdly formatted characters and changes them into their plain standard versions, right? So if you write a number 5 in a fancy circle like 5 and then circle, and a superscript like 5, the NFKC strips of the circle or the file sizing and turns into plain text normal 5, and then it will do composition. Finally, NFKC takes all these clean standard bricks and pieces them back together into a single character shortcut. Character if one exists. Like it puts the Lego bricks together, but it's time it is used to official manuals, so every single house looks exactly the same. Okay. So this is how it works. And the next thing we do, guys, is here. Okay, and then we have our pre-trained tokenizer also. Tokenizer dot pre tokenizer. Okay, it will like pre-sequence. Okay, what it will do? It will white space comma punctuation, and punctuation we have behavior is equal to isolated, right? What is this, guys? Let me tell you. Okay, this is very important. Like this will happen before the PPE, right? The two main pieces are there, like white space and punctuation. So white space splitting helps the identify basic word like segments, right? Like for example, we have this word like I love LMA, right? So we can conceptually separate I love LMA here before applying the learned subword merges, right? So we can separate them here only, this like that, right? For example, in the punctuation, what it punctuation will do? Let's say you have this LMA then apostrophe. So instead of allowing a learned token such as this as a whole token, what it can do? It can split this LM then already, right? We don't have to learn this. So this will make the punctuation reusable, right? And we have the one flag here, isolate also, right? As you can see here, isolate. Why we are using this flag isolate? So the original scripts make this point that this stops the merges from gluing punctuations into words, right? For example, we have this LMA apostrophic and LMA, right? This should not necessarily become permanently fused, right? So the tokenizer can represent like LMA and this more flexibly, right? So that is it. This is our the build tokenizer, guys. Okay. Okay, and then I can return tokenizer here, right? I can return it also. This is our full build tokenizer now, right? Now next thing, we will train the real tokenizer, right? Def train, it will take a tokenizer in it and some files, and we have to define the vocab size also, how much vocab, and we have to define the minimum frequency also. Frequency, right? So vocab size, like what is our target? We already have our target, which is 30,000, but we can like define it also, right? And so why we are taking 32k vocab size, guys? So there is a trade-off here. If we have larger vocab size, right, that will mean like we will have longer subwords, okay, and fewer tokens as per sentence also, and we have the shorter sequences and more efficient context uses, okay. But if we have large vocab size, then we will have larger embedding matrix, and then we will have more model parameters in that case, because our model is only around 120 million parameters. So vocabulary size matters here, okay. So suppose, let's say make the connection of mathematics and here, right? Let's say we have vocabulary size of 32,000, right? And the embedding dimension is 768, right? So then the token embedding matrix has approximately token embedding matrix has approximately V cross D parameters, right? So this is will be approximately, it goes to 24,576. These number of parameters, like approximately 24.6 million parameters. This is already a large fraction of our 120 million model parameters, right? And this is why tokenizer vocabulary size is not merely a pre-processing detail. It will affect the model architecture, right? So here that is, and we are using the minimum frequency. What is this minimum frequency here? This will mean that minimum frequency is equal to this minimum frequency we are using, right? This means that we can ignore very rare pairs. For example, like if some pair have like a minimum frequency is 2, that means pair occurring only once may be ignored, right? The pair must have at least 2 frequency. So this will reduce the noisy or unnecessary vocabulary entries for us, okay? And we have this special tokens in our vocabulary. Special tokens is equal to this special tokens from here, right? This tells the trainer to reserve the special tokens we defined earlier, okay? And okay. Okay guys, thank you so much. I will meet you tomorrow, okay? And in the next class. Thank you so much for watching.